In this video, I will keep talking about two-dimensional maps. And let me first remind what we did so far. So far, we're considering linear maps. Linear map. Linear map looks like this. Un plus 1 vector u equals matrix A times un, where un is vector with components xn and yn. And here what we found that there is linear map has only fixed point. We can easily find so vector u equals to 8 times vector u. So this is equation to find fixed point. As you can see, this is equation basically for eigenvectors and eigenvalues. So we can rewrite it like this: a minus I times u equals to 0 vector. And you will have, it has the only solution, which is u equals to 0, 0, if determinant of this matrix A minus I is not 0, if this matrix is not singular. And from here, eventually, it can be derived. So this means that none of eigenvectors, eigenvalues of A is 1. And for this, what we found that so 0, 0, 0, 0 is a fixed point whose nature depends on eigenvalues of matrix A. And particularly, if lambda 1, 2, both of them perhaps less than 1, then 0, 0 is stable node. And if lambda 1 and 2, they both more than 1, 0, 0 is unstable node. And if one of them is less than 1, and another one less than 1, and lambda 2 more than 1, this is saddle. And if lambda 1, 2 are complex conjugates, dependently of initial conditions, of initial point, orbits converge to 0, 0 or not, depending only on lambda 1, And now let's talk about nonlinear map. Linear map, xn plus 1 equals to f of x yn, yn plus 1 equals to g of xn, yn. So fixed points are roots of the algebraic system. X equals to f of xy and y equals to g of xy. So there can be many assume x capital, y capital is a fixed point. Then let's say it's somewhere here. X, y, let's say this is x capital, y capital. Then we can analyze behavior or orbits in the vicinity of this fixed point by linearizing the map. So what does it mean? It means that we can introduce two other variables, epsilon n, which is xn minus x capital, and delta n, which is yn minus y capital, and assuming that epsilon n by absolute value very small and delta n very small, then for epsilon n and delta n we will have linear map. Epsilon n plus 1, delta n plus 1, this is a vector, equals to some matrix which is called Jacobian times epsilon n delta n. And this Jacobian was introduced last Wednesday on our online session. You can look again what the proofs. I even gave a proof by these swaps. So here, where J is called Jacobian, and J is given like by partial derivative of f over x at x capital, y capital, derivative of f over y at x capital, y capital, g, derivative of g over x at fixed point, and derivative of g over y at this fixed point. And now x, y is fixed point whose nature is defined by eigenvalues of matrix J. So Xj is a fixed point whose nature is defined by eigenvalues of Jacobian J. And everything will be the same as before. The only difference is now, so X, Y, again, can be stable or unstable node. Saddle, stable or unstable focus. And now the difference is that whatever we say, so this was X capital, Y capital. So now somewhere here, so we can conclude about dynamics of the system only in the neighborhood of X capital, Y capital. So somewhere here, because this any point here in neighborhood, so there will be, so this is, for example, point xn, yn, but this position of this point is defined by its position relative to xy, or by two small numbers, two small components of this vector, epsilon n and delta n. These two components is components of this vector, which is difference between x position vector x and y n and position vector x capital y capital. Now, so this is first difference, only neighborhood, and second difference, what happens between fixed points. So second difference was that we can have many fixed points. And here, for global, for analysis of orbits far from fixed points, we consider saddles. So how it works? Let's consider saddle. Let's say x capital y capital is saddle. Therefore, we will have two eigendirections, p1 and p2. And if we started somewhere here, so since one of eigenvalues is more than one by absolute value and another is less than one, we will have this kind of motion. So, for example, towards B1. So this means that lambda 1 by absolute value less than 1, lambda 2 by absolute value more than 1. Then there will be this kind of patterns. So, so no matter where we start, it will, so component of position vector along eigen direction B1 will be shrinking and along eigen direction B2 will be extending. And so these two, again, if we started on line B1, there will be motion towards saddle point. If we started on the line B2, it will be more motion away, but in between there will be some kind of motion towards. Generally, there is from any other point, there is a motion towards line or B2. So this is B2 is a straight line for linear system. For nonlinear system, it is not necessarily straight line. So this tangent to B2 is eigenvector corresponding to eigenvector B2. But for nonlinear maps, generally it is so B2 is only approximation to this line where along which orbits go away from saddle. So this is only approximation. Approximation is straight line, but in fact it's bended. So this can be bended, and B2 also can be bended. So generally, I can put it like this. So this is B1 line, this is B2 line, and this is saddle point. So if it's saddle, then we have motion away if lambda is more than 1 by absolute value, motion towards if lambda by absolute value less than 1. And again, so this is called stable manifold. This is called unstable manifold. What is important, so this is fine. If we have assume, so this is saddle, fine. Assume somewhere here we have this is, let's say, stable node. So in addition to saddle, we have stable node. Then since all orbits get closer to points on B1, to line B1, this means that if there is a stable node, which is attractor, it should be on line B1. So this is stable node. And so this orbit, so there is an orbit which can start at B1. There is an orbit starting at saddle and ending at stable node. So this is called heteroclinic orbit. So this is main conclusion when we consider saddle. So if there is a saddle and there is a stable node, for example, we have only two fixed points in our map, then stable node will be located on unstable manifold of saddle. And there will be a line connecting, saddle and stable node such that if we have an orbit, so it will represent an orbit which originates at saddle and ends at stable node. And same is true about unstable node. Unstable nodes is located on stable manifold of saddle. And this way we can analyze dynamics in this system when in between of different fixed points. And we did it last Wednesday when I was considering an example of nonlinear map.